Hi, hello all. In this video we learn about the basic image processing, and in the first section we learn about image basics. What is image, how to convert the color from RGB to gray to binary. Then we learn about how to change the brightness of the image and how to alter the contrast. In the interesting second section we learn about the image operations. So the very simple and important operation, we call it as morphological operation. And then we learn about convolution. So it's not a traditional convolution what we see in other channels. This is a convolution which is specific for computer vision image processing, and it will be so application oriented. Then we learn about edge detection. So here edge detection we have come across from convolution. Then we learn edge detection through convolution, and also we learn about blurring the image, and finally we will do one toy application, how to change your selfie image to a pencil sketch. And let's go to the video. What is image? Image is a matrix. So it is not the movie matrix, but it's a matrix which is a data representation in rows and columns. Let's get a grayscale image. This image we have used a lot in the previous video, how to read and write and how to see the images. Let's take a small pieces from this corner, and we can see the numbers, how this corner is represented, and some values, numbers, right? It's numbers. You cannot see an image in these numbers, but how a system display image or how it saves the image from this gray shade. Okay, so if you have a 0, then it's complete black, and if you have a white, it will be represented by 255. So 0 to 255, and you have a lot of shades, and each shades depends on the number which we get from here, and it will give the color for you to see things. And you should know about the row and column. So the row of an image and column of the image, they will call it a shape. So the row represents the y-axis and column represents the x-axis. Through this row and column you can know the resolution of the image. In your videos, in your image, you can get something. So if you have a mobile camera having a 24 megapixel, then it's like the image get from the camera, the height and width. The row and column of the image we get has 48 megapixel. It 48 into 10 to the power 6 pixels it has. So image resolution will be represented by the rows and columns of an image. This is a grayscale image, so only one channel. Color image. So color image is similar as grayscale image. It's having rows and columns, but it has more than one channel. So let's see here a red channel. So here all the red components, the colors, red color information will be provided, where if you see a black color, it's 0, where no red color components. You can see here black color, and in the top right you can see a white. So some of the red color components are there. This is our green color channel, and green color channel will have only the green. If 0 means there is no green component, and if 255 there are full of green component. So here, yes, there are very light green components are there compared to red, but here you have less green components. And black color is 0, no green component, and white color has some green components. Yep. The final one, the blue, yes, here you can see the whole the sea, the trees, consists of lot of blue color component. Here this area in all the image as their components, it's like a white consists of all the colors. And you can see the dolphin area where every image is black because no red component, no green component, and no blue component. Okay, so a color image will be represented by 3 channels, so red, green, and blue, and it has 3 dimensions, we can say. So one is row, another one is column, and another one is channel. Binary image means 2. So with 2 types of pixel we can represent an image. So this is a binary image where the black color is represented by 0 and the white is represented by 255. Can you imagine a nice photograph can be represented by a binary values? Yes, we can. So here this is a nice image from Wikipedia where you can see 2 colors, 0 and 255 can represent an image nicely. The density of the white and black dots represents a grayscale color. In the last video we have already seen how to read an image, how to write an image, how to show an image on the screen. So if you want to see this video, you can click the description or on the top corner about the previous section. Okay, let's now create a Jupyter notebook using Visual Studio Code. Ctrl+Shift+P and you can type Jupyter notebook. Create new blank notebook. So compared to classic Python py, Jupyter notebook is used for researchers, someone who wants to try new things, something you want to check how it works and how the input and output, how your function works. You can visualize things, you can analyze things using Jupyter notebook has been created. Ctrl+S to save as a new file. Let's save as basic image processing. And a new file started. So the very first already we have seen. Let's import CV2 as CV, and also we import CV2 numpy as numpy. And here we are going to learn another new library. Import matplotlib.pyplot as plt. So these 3 libraries we are going to use. Shift enter, so this whole file will be completed, this whole section will be executed and it will complete. So if a star mark is here, then it means that the whole section is running. Okay, let's read an image. Yes, file name equal to, so here already we have the dolphins JPEG. So right click and copy path and paste. You can use Ctrl+V. Then I already explained you, like in Windows the slash which we are using will not be supported in Python, so you have to put R in front of it. And I am completing this sentence, so shift enter. now we are going to read an image. So let's read as learned the previous lecture. Page read, file name, okay. So now we are going to visualize the image. So now the matplot library comes in. Plot, I am show, I am H, shift enter. Okay, you can see the image now. Do you feel any change here? Yeah, the water looks yellow, but the real image the water doesn't look yellow. The water, and it's some color change you could understand. Yes, it is because OpenCV reads and keep the image in BGR format, but the matplot library and all the other programming languages, they are always using the image in RGB format. That's OpenCV will be in BGR, blue, green, red, but the real everyone uses the red, green, blue format. I will explain you in coming session. Okay, so I want you to learn conversion, how to convert an image. Already we have seen a lot of image types in the previous video. Now let's see the conversion. A good thing in Jupyter Notebook is we can write your own text. So you have to click this button and you can type your mark down here. Conversion of image colors. So if I have I will do without the star hash. So you can see this is not a Python code, but it runs like this and it types what you are typing. If I want to change something here, I want to make it as a header, so I can put one hash in front of it and it's a header. That's a very big header. If you want to have further, a small header. So this is much useful if you learn something, or if you practice something, or if you are doing analysis and you want to show to your superior or your the person who is interested, and it's very nice to have a heading like this. Now we are going to learn how to convert image. So now we are going to convert the image BGR into RGB. BGR RGB image equal to CV convert color CVT color, and now I am going to give the source, that is image. Then I am going to give the color which I want to change. So it's like CV dot, it's a enum. So CV dot color underscore BGR 2 RGB, and you can also have two lines to see the image. Plot I am show RGB image, and shift enter. Yeah, we can see the real image. I already explained you that OpenCV reads every image in the BGR format, but all other tools except OpenCV uses RGB format. So Matplot library uses RGB format. Once you get the RGB format and give to the IMShow, it gives the correct image. Okay, already we have seen in our slides we have seen grayscale image. What is grayscale image? Can we convert this image to grayscale image? Yes, let's see. Grayscale image equal to CV convert color RGB image, comma, and CV dot color RGB to gray, and we are going to see the image. Plot, I am sure gray image. Oh, so gray image always have a color. It looks similar to black and white, but you know there are different intensities. But you could see here the image is not a black and white image. It has a green color. It has somewhat not a black and white image. So the reason is the MATLAB library I am sure tries to show everything in color. So we are going to change the color map, that CMap equal to gray. Okay, now this is the way how we see the image, gray image. Now you can see right the same image in a black and white TV. So in olden days we have the black and white TV, right? So it's similar way we can convert any image to RGB, HSV, BGR. There are a lot of formats. I can say what are the formats available in OpenCV. You can see LUV, RGBA, RGB. So these all formats each can be used for different operations, where YUV is hugely used for transforming signals in through antenna, TV and everything, and BGR 555 it uses for embedded devices where the highest bit number is 5, where all others we have 8-bit intensity. I will explain you in coming section. Okay, here you can see right now we want to see how this image look. Okay, what is pixel? Why people say image is a matrix? So I am changing this to a markdown format. Shift enter. Yeah, now we are going to understand what is pixel. So let's see, I already told you, right? So let's see what is the size of this grayscale image shape. You can see it's 2919 rows and 4374 columns. So there are around 2919 rows and 4374 columns. Okay, so any image, so it's a matrix, I told you, right? So the rows and columns are this. Let's take the first 10 rows and first 10 columns, like the small corner. Let's take and let's see what's the pixel values. Grace image square bracket 0:10 and shift enter. Okay, now we are going to see a single pixel value. So I'm going to grayscale, gray image, 100,100, and shift enter. You can get the number. Okay, so in the 100,100 we'll get the value of the grayscale is 126. In grayscale, a pixel will be denoted by only one number, and the number should be in between 0 to 255. Okay, so you can see all the images, all the numbers here, everything, it should be in between 0 to 255. Why 255? Yes, 256 is a number which can represent by 8 bit. So 256 is some common number to represent 1 byte. So if a grayscale of 100 cross 100 size, then number of bytes it needs is 100 cross 100 bytes. So it's around 10,000 bytes it needs. So you can calculate our image size with respect to the pixel size. So each pixel is 1 byte. That's 8 bit. Okay, let's see color image. Okay, so if you want to see the color image here, okay, the same size, I'm going to type RGB image 0:10, 0:10, and shift enter. You could see down, oh, there are a lot of pixels. Okay, you know, every pixel has three bytes. Okay, so I will explain you nicely. I already told you in the section that we have red, green and blue colors in a single image. Okay, so now I am going to show you how a red color. You put 0 here. Yes, this is our red color image. If you put first, this will be our green color, and this will be a blue color. Okay, this is a channel. So we are seeing a numbers you couldn't understand. Let's see how it looks like. Could you notice here that I'm adding another variable, right? This is a channel. So row, column, channel. So it's a 3-dimensional, and third dimensional has only 3: red, green and blue. Okay, let's see how to receive a single pixel. Hundred cross 100 and press enter. Yes, as I told you, right, here a single pixel in color image will be represented by 3 bytes. Okay, you can see each byte will be in between 0 to 255. So this is a 143, this is a red color, and 120 is a green color, and blue color is 112. Okay, so a pixel will be represented by 3 bytes. This is interesting, right? Let's see the visualization of each channel. Okay, okay, before going to know, right, so I can plot a red channel, RGB image. So I want to use all the height, all the rows. I just put 1 colon, then comma, all the columns, colon. Then I'm going to only take the red color, so I'm taking 0. So all the rows, all the columns, I have to put just colon, colon, and I'm going to get only one channel, 0. Okay, and I'm pressing shift enter. Yes, you can see the red channel here, gray, and shift enter. Yeah, you can see this is a red channel, and yeah, you could see here. So some area there are some reds, but most of the area it's black in the sense there is no red particles in the screen. Okay, let's see how other channels are working. But before that, right, so if I want to see multiple images in same row, how can I do it in Matplotlib? Let's do it. So there is one concept called subplot. So I'm adding subplot. So I want a single row and I want 3 columns. So here one image, next image, third image. So 1, 3 column, and this is my first image. So the first 2 represents the number of rows you want in the visualization and the number of columns you want then first image. Now I'm copying this, duplicating it, and changing this to second image. And yep, second is a green channel. Okay, then now I'm going to paste the blue channel. So blue channel is the second 2. So all MATLAB, OpenCV, NumPy, the indices starts with 0 and end with n-1. So here 3 channels and it starts with 0 and end with n-1, like 3 minus 1 is equal to 2. Shift enter. Yeah, you can see yep, all the images, all the 3 images, red, green, blue, are coming on the same row. But is it interesting? No, let's visualize in a bigger view. So same pyplot, figure, and I'm going to give fig size 25,25. So one cool thing here is like you can test it your application Jupyter notebook and you can correct it again and you can test it again. Let's wait, it's still running. Yeah. So now you can see the big picture of 3 channels where this is a red channel, red particles. Yeah, in this image you could see here there are very less red particle only on this area, somewhat red particles are there. So you could see here somewhat white and all others are black. You can see here, yep, some green and blue mixed colors are here. So here this is a green particle. So green is everywhere but very little, I could see here. And this is blue. Yep, you can see the whole, the water, the sea water looks very bluish. So you know here blue is so white compared to this image. There is no red particle, so it's black, and some red particle, it's some lot of blue particles, so it's very bright here. So in this way we can see how the colors are there and how colors are arranged. So very first we learn how to change the brightness and alter the contrast. So if you add any pixel or if you subtract any pixel in the image, not a one pixel, all the pixels by one constant value, then you can increase or decrease the brightness. So just adding a constant that we call it as brightness factor. If you decrease, it will, the image will become dim, and if you increase, it will get more bright. The next one is contrast. Contrast, instead of adding, we are multiplying it with a constant. So we are giving a contrast factor about 0 to 10, where if you want very high contrast, please give 5, 7, 8. If you want very low contrast, you give 0.01 or 0.05. So very small value will give a low. So if a contrast is lesser than 1, so we are reducing the contrast. So in this way, this is the formula how to do a contrast and also alter the brightness in an image. So just multiply the image with the contrast factor and add the brightness factor. Let's see how we do in our Visual Studio Code with OpenCV. Now we will see how to change the brightness and contrast of the image in OpenCV library. So I am making a markdown to make a section here. I named it as brightness and contrast. So, and also it's a good practice to have the formula inside here. So output image equal to input multiply by alpha plus beta. So please always keep something in the markdown like what you are going to do. This will help while you reverse your subjects again. Shift enter, as you can see. So to have a better understanding, I'm going to load another image. So let's have file name here. File name, I have an image here. As you know, copy the path and paste the path, Control V, and I put R in front to avoid the Linux Windows conflict on file path. Then we have to read an image. So same image, gray image equal to CV I am read and file name. So here I'm adding another type of reading. So instead of always reading an image and converting an image, we can directly read a grayscale image in OpenCV. So I'm doing that. CV load. So CV I am read. So any color, any depth, color. Yeah, there is one thing called I am read grayscale. So I'm going to read I am read directly grayscale here. Yeah. Now we are going to do the equation, right? We already have an input into alpha. So whatever a best learning, a best practice to implement a function, implement a formula, please make a method, a function here. So define brightness and contrast. So here three inputs. One is input image, alpha and beta. The very first thing is I'm going to convert the input image from unsigned integer 8 into a float. So NumPy helps this. So I'm changing the input image, create a new image, np array input image, comma np float. Then I'm applying a formula here because after we convert the float, then we can use a formula. So my output image, so I keep it amount of page equal to image into alpha plus beta. then right, so if my input value, the pixel value is 200 and my alpha is 2, so 200 into 2 it will be 400. But I already told that an image should be 0 to 255, a best image. In the current computer vision and image processing, everywhere we keep 0 to 255 as our image range value. So I am clipping the image, like if I have 200 into 2 it will be 400, but I am clipping into 255 that. So I'm using a numpy's clip function, out image, comma, the minimum value will be 0 and the maximum will be 255, and my out image, and I'm returning this out image. Okay, so shift enter to confirm this function. Now this function is executed. Let's run this function. Okay, just my modified image equal to brightness and contrast, input image will be a grayscale image, and yes, I want to make a separate variable for alpha. Let's keep alpha as 5 and beta equal to, the very first we'll make it 0. Okay, don't keep alpha as 0, so it multiplies with the image and always gives a 0 image, black image, and my alpha and my beta. Now I want to see the image, so first thing, I need to make a nice view. I have to compare how it changes. So my plot figure, fixed size 25,25 is best. You can play around in later stages. Then I am having a subplot. As I told, I want only one row and 2 columns, and this is the first image. Then I'm going to show it. Now I'm going to only show the input image. So as we know, right, the grayscale image, so I need to apply the CMap gray. Then I'm going to show another subplot. This will be my modified image, and same 1 row 2 column, and this is the second image. Plot I am show, and my modified image comma CMap equal to gray. Let's see, shift enter. Okay, here you could see, right, this is the input image, and I increase the contrast to 5 times. You can see, yeah, it's cool, right? You could see some small, small hills, great, right? But in this image you couldn't see this, but you can see here. Yeah. Oh, so I increased huge contrast. So what happened, right? You could miss, this color. Okay, you have missed this, right? You haven't seen any boards or any small things in this area. It's completely white. Yeah. Okay, let's change let's keep the alpha 1. So alpha should be 1 to 0 to some value. It should not be less than 0. It should always above 0. Okay, it should not be 0 and it should be above 0. Okay, let's see the brightness. So I'm going to change the brightness. Now I keep the brightness, let's keep the 10. Okay, 50. Okay, so it's a pixel value. I'm adding some 50 values in the brightness. Shift enter. Okay, so brightness is cool, right? So you can have a nice bright here compared to this. Yeah, so brightness is perfect. It's like most of similar but very small increase in the value. Yeah. Okay, let's give a high number. Okay, so let's give 100 brightness and shift enter.
Okay, you could see a lot of changes here. Here it's this area, the boards where we see here, you could see a little more bright, and it looks like we are giving focus on this area where more whites. Yeah, and all of this, yep, it's common. It's not too much white. We couldn't see the hills, but this area is well defined and focused. Yeah, you can. Now I have given the clue how to use brightness and contrast. You apply in your own selfies, you can apply in your own photographs programmatically and enjoy this.
Morphological operation. Morphology means study of shape. Here what we are going to do is we are going to change the shape of an object in an image. Here we are going to cover very important two morphological operation. One is dilation, another one is erosion. So what is dilation? So by the name dilate means is spreading. We are spreading a shape in the image. Let's see how to do it instead of explaining what is this. Okay, let's take a grayscale image. This is one of the grayscale image, and we are seeing the numbers of the grayscale image. And here in the dilation we want a kernel. So this a small 3x3 of ones, we call it as kernel. Here the 111. So we, for dilation and erosion, we expect the kernel value should be 111. So here 3x3 matrix, and we are keeping the 3x3 in 1 pixel here, and we are checking all the pixels neighbors. So in this, let's take this pixel, center pixel, and we are taking the neighbor, and we are getting the maximum. So the dilation process is getting the maximum of the neighbors and replace the center. Let's say one example here. So here 118, this is our center pixel, and what I am going to do is I will go and see all the neighbor pixels, and let's say which is maximum as 124. So what I will do is I will replace this 128 into 124. In this way we will do all the pixels in the image, and we will replace it with the maximum with respect to the center. So how it happens is it will start from the top left, and it will go to every rows, and it will replace the pixel with respect to the neighbor. So dilation is nothing, just replacing the pixel with the maximum of its neighborhood. Okay, so let's see how the values here after applying the dilation. Okay, so let's see here, when we keep this kernel at this place, we omit the outside thing, and we see here in this first corner which is maximum, in this first corner which is maximum at this position. So you can 100 is a maximum. I'm going to replace it with the 100. Then you can see here 100. Then I am checking the next set of kernels here. So I'm going to check this set, and here there is no numbers, so just leave it. And here in the next one also we could find that in the whole neighborhood 100 is maximum, and I'm giving 100. Okay, in this way we'll fill every pixel here. Let's take some pixel in this area. So let's take here this pixel, and I'm going to check the whole neighborhood. It's 3x3, and you can see which is highest here. Yep, 135 is the highest one. This is my highest and maximum at this neighborhood. So you can see here we have replaced that 120 with respect to this, we replace with 135. In this way we'll replace every pixel with respect to the maximum of its neighborhood. So let's see what is dilation. Yeah, deletion, the same principle, same action, but instead of taking the maximum, it will take the minimum. Okay, you can see here, these are some other example. Like I can take some example, same 120 I will take here. So in the 120, and I'm taking the surrounding pixels of the neighbor, and I'm checking which is the minimum value of all. The smallest value, it's 117. So let's take this 117, and here we will replace it with 117. Okay, so this is called erosion. So very simple. Deletion, it will take the maximum of the pixel with respect to the kernel's neighborhood, and erosion, it will take the minimum. So what will happen, we'll see in the next slide how the deletion operates and how the erosion operates. Let's see the morphological operation in action. So let's take a binary image where one circle and one square here. This is a binary image. Here everything is 0 and center everything is 255. And once we apply deletion here, you can see there is a spread of the circle and square. So the size is increased with respect to the shape. So you know what happened, right? So when in the borders area where the white will replace as a maximum value. Let's see how erosion work. Here once we erode the image, what will happen is the image has reduced. So we are applying erosion on this binary image, and once we apply the binary in the error, and we are taking the minimum of the surrounding, and the image is getting reduced and becoming very small here. So when you want to change the shape of the mask image processing, we can use this morphological operation. Now we are going to see the morphological operations next version. So it's a derived morphological operation. So same image, once you apply a morphological operation in a continuous format, like deletion followed by erosion, we will call it as close. This is most common one in image processing, because you know you want to fill some gaps, some unwanted things inside the image. You can see here a small dot is the circle in the real original image, but once you apply a close, what will happen, this part will be filled. Okay, it is filled because a dilation, but a dilation combined with erosion, what is happening, this small hole is filled, but the shape is not changed. You can see it is preserving the shape, so it is just closing the gap. So through that, you know, it has some artifacts, but when this is not there, you can see the exact image, but only the hole is filled. So if you want to fill a small unwanted things in an image, you can use I am close, image close. The next one is called open. So close is closing the gap, open is opening if any unwanted things are there. Okay, you can see we can't see something here because there is not a good example to show this hole, but you know, once you apply a erosion followed by a deletion, what happens, you could see here there is no changes. You know, the whole image is as it is. It didn't close this, and it doesn't increase the shape or decrease the shape. What happens when I will show a very nice example, hands-on training, and you can see what really happens when you apply the close and open morphological operation. Let's go into the action of morphological operations.
Let's create new Jupyter notebook. Ctrl+Shift+P. Create new blank notebook. Wait for let the server starts, and you can save it as Ctrl+S. Morphological operations. Yeah. So the model is ready to start. The Jupyter notebook is ready now, and as usual we have to load the basic CV to a CV, import numpy as mp, import matplotlib.pyplot as plt space and shift enter, as now these models are ready. Then now we are going to create a binary image. So binary image, as we told, right, the lowest will be 0 and the highest will be 255. So the first we have to make a markdown, binary image, shift enter. Now the heading appears. You should always document your tryings, then it will be easy for revisit things. Now a binary image, so always use underscore in between variables. Numpy np zeros, shape equal to, let's keep shape as 100 cross 100, and shift enter. Yes, we can see our image. So I will show the image. I am show binary image, very important, cmap equal to gray. Okay, shift enter and you can see your black image. Okay, so you know, a black image, everything 0 0 0. Now we are going to draw a circle, a rectangle and a line. It's interesting, OpenCV supports this thing. CV circle, the image, that is binary image, center, let's keep it top corner 25, 25, and the radius, yep, 25, and color, yes, 255, as I told it should be a white color, and the thickness, yes, for if you want a circle, you can keep the thickness 1 2 3 pixel, but if you want a circle filled with the white color, the color what you provide, you can give -1. Next I'm going to draw a rectangle, type binary image, point 1, so x comma y, point 1 x comma y, we give it the center, then somewhat right corner, and the color 255, and the thickness, yes, I need a filled one, so -1. Then CV line, I'm going to draw a line, same binary image, comma, point 1 for this. Let's draw a circle from the center, sorry, a line from the center of a circle, 25 comma 25, then the starting point of the rectangle 50 comma 50, then color 255, and thickness, yes, for line you have to provide the thickness, and I'm going to give a, let's keep us 2. Okay, yes, and let's see the image, binary image, comma cmap equal to gray, shift enter. Yeah, you can see a circle on the top 25 comma 25 center, and a rectangle from center of this to 80 cross 80, and yes, a line from center to the starting point. Yeah, you can do a lot of diagrams, you can play around with OpenCV now. If you have a color image and you want to give a color, you can, instead of 255, you have to give the RGB in a tuple. Okay, now what we are going to do is we are going to do the morphological operation. So morphological operations. What are the morphological operations we are going to do? Deletion, erosion, close, open. Okay, so I need this marked down. Okay, excellent, good. Okay, now what we are going to do is first we are going to do a deletion. Very first in the deletion process is creating in the morphological operation is creating a kernel. So I'm going to create a kernel, numpy once, and the shape, let's keep the shape as yeah, let's keep as 7,7, let's keep 9,9, and yeah, that's enough. Now we are going to apply a deletion and erosion. Okay, OpenCV has a deletion and erosion APIs, so it is easy for us to call that function. So deletion image equal to cv dot delete, and the source, yep, the binary image is my source. The kernel, yep, I have a kernel. Next what we are going to do is erosion image cv.erode, and as usual our binary image will be the input and the kernel will be the output. Now we are going to see these things. So I am assuming that I want to see the image and the deletion image and erosion image in a single row, so too easy to compare with each other, we should keep in a single row. So I'm making a figure with a fixed size 15,15. So some hard rule, right? If you keep 15,15 and you can see 3 images nicely, if you increase you can see much better. If you give 25,25 for 2 images, but it's your wish, you can play around. Now I'm going to have a subplot. As I told you, 1 row 3 column and the first image, and going to show the image, a binary image, comma C map equal to gray. Yeah, good. And I don't like to type again, I'm just copying the last 2 lines, and because I'm going to show this here, the second one here, what I'm going to give is a dilation image. Please try to copy and paste whenever it's possible to save time. Okay, now shift enter. The star represents it is processing. Now it's completed. You can see that there's an image and dilation, and you can see dilation, yes, dilation spreads, it spreads the binary positive, that white color 255, and when you don't, as name suggests, erode, so it's a apply erosion, and you know it is reduced and the small line has gone because small things. So in computer vision morphological operations, as this basic morphological operation, what it happens, right, when you want to increase the size of any mask or any informations or anything in image, you use morphological operation deletion, and if you want to reduce the size or remove small unwanted touchings, right, you can see here a small line, so it's unnecessarily touching, so we want to remove that, you can use erosion. But let's see the further one, derived morphological operations. Yep, I just derived we are going to see two derived morphological operations here. The first one is I am close. So before that, I want to draw something little nicer. So we are drawing a white color, but I want to draw a black color circle. Let's see, binary image equal to CV circle, sorry, CV circle, and binary image comma center, same 25 comma 25, but my radius I want very small one, so let's keep 5, and the color 0 because 0 is the color for black, and thickness -1, and let's see that. Okay, a small circle. Okay, let's do the closing. So closing is a process of dilation followed by erosion. Okay, so I will type in the markdown. Close equal to dilation followed by erosion. Okay, same kernel we use, and yeah, so close image equal to CV. Okay, so there is no separate function method to call for in OpenCV, but we have a morphological operation things, so we'll call it as morphological extended version, and the source here binary image, and the operation right here, the operation you have to give us CV dot morphological operations close comma a destination or kernel, and let's give a open image CV dot morphological binary image comma CV dot morph. If you type morph, you can get the open and kernel. Okay, now we are going to see this, but I want to see as this picture, so I just copy some pieces of code. Yep, and I'm changing things. Binary image is binary image, and close open image. Shift enter. Yeah. Okay. So you can see here the first one is our binary image, and this is a close. Okay, what close does is closes small things. Now the names, this is nice, right? So it closes small things, but it is not removing like erosion. Okay, like dilation, it will big. In dilation it will big, but it is not applying any dilation where it will big. You can compare here in this image. 1 minute. So here, right here, the dilation it will be big. It is big. It is very big compared to the close. Yeah, it closes the small circle, but it is not removing unwanted things. In open, what it does, right? It is keeping the things, but it just removes a small thing. So the size it is same. It is not removing or sinking, where in erosion it is shrinking. The size, everything is shrinking, but it is keeping this thing, but it is removing as small joints. So please use close and open in lot of places. It helps to keep the morphology, keep the structure shape, and it removes what we want. It adds something, it closes something.
Convolution. I don't want to complicate convolution by theory, but you can simply understand it by its usage in image processing. It is a process of finding a pattern or characteristic of one matrix on another. So if I want to find a line, or if I want to find some circle like feature, whatever we want, we can find the pattern on the image by using convolution. The pattern is simple kernel matrix and image is another matrix. By applying convolution, you will get a highlights where the patterns presents. Implying the characteristics. So if you have a pattern and you want to imply that pattern to an image, instead of saying a pattern, I can say if you have a kernel and you want to imply the kernel on an image, a kernel as a blur one, and you apply convolution the kernel on the image, you will get a blur image. The same thing, if you want a sharpened image, you have to create a sharpened kernel and apply it. Let's see the very simple theory from the convolution. I don't want to waste your time. So here this is an image, grayscale image. Here only we are showing the pixel value to understand better. And this is a kernel. This is a simple kernel where a single line in the center, which is a horizontal one, and top and bottom are 0 0 0. I am going to imply the characteristics of line and find the pattern on the convolution. So it's very simple. I just keep the kernel on the top of the image and multiply all the values with the neighbor of the pixel, including the pixel, and sum all the values and replace the center. So I'm saying again, I'm just multiplying all the kernel values on the pixel neighborhood and multiply it, then sum, add everything and replace the center value with the accumulated sum value for all the pixels from starting pixel and replace the starting, and it's same as the morphological operation you have to do from the top row, top column, and you have to process from row by row by row, and we have to end at the end. So I'll explain you with a real example here. Let's take one number here. Let's take a 98 here. Okay, this is my center pixel, and I am taking all the pixels around this. Okay, and I am multiplying all the pixels with a we will call it as kernel's numbers, kernel weight. So I am multiplying the value with the kernel weight, so you can get right. So here you will get 97 and 0, you'll get 0, and then we'll get another 0 here because 98 plus 98 is 0. Then here this 98 plus 0 is also 0. Forgive me for my handwriting. Here then I am going to have some value here because I'm multiplying with 1, and it will come as 97, and then I'm multiplying the center pixel with the central kernel weight, and it is 98, and here 1, so here also 98. Then the last row with the last row of the image neighborhood, so it's everything is 0, so 0 plus 0 plus 0. So finally 0 0. I'm drawing with the mouse, so I cannot draw clean there. Okay, so totally you have all our zeros here, and so you want 293. I'm not sure that's I'm right. So 16 plus 7, yep, 3, and 3 9s are 27 plus 2, yep. So 293 is our value here. So once you do the convolution, and we will replace the center pixel. By this we apply to all the images, all the pixels, and you will get this value. Let's see the value of this 98. So it's a third row, second last column. So third row, second last column. Yes, this is the value. Okay, so once you apply a convolution, you will get this value. Yeah, how this will helpful? Let's see in the next slide. Finding the pattern. So like previous slide, we have seen that we have a horizontal corner and an image. So instead of using grayscale, I'm going to show in an image, and this is a black and white image, and just I have drawn a rectangle square here, and I'm going to apply the kernel. So how this kernel looks in the image, it's simple line, as I told. Once you apply this kernel on this image, you should find the pattern of this kernel. Okay, let's see how it reacts. So once it goes, it only gives some value when it is here. It may give some value here, but all other places it should give 0. Let's see the output here. In this image here, you could find the line. The line is the pattern. This is our pattern, and this pattern is being found in this image. Okay, but you can see that there is some small unwanted thing is there. Yes. Okay, so what this artifacts? Okay, this artifacts nothing but it has the one. Okay, it has some informations, like not every information, but it has some information. So it's not the line, but it has some information. That's why a blurred information is there. When you apply a threshold, you can remove this, but all other places you get a complete 0. So when you apply a convolution, just multiplying with the kernel weight with the neighborhood of the pixel and replacing it, you will get the pattern. Let's see how to apply our characteristics on an image using convolution. So let's take our logo image, a grayscale image here, and I'm applying a convolution here, and this is a very plain kernel. The kernel weights are just 111, and it's very complete plain. And once you apply a convolution, you can see a blurred image. You can see it's a blur one. How to blur an image? If anyone asks, yes, I will apply a blur kernel on it, and you get a blur image. So blur kernel is nothing, a plain one. If you apply it, you'll get the blur image. It's nice. So let's see another example here. Okay, instead of blurring, let's apply a kernel which is a little different, where it's somewhat impulse like kernel, where at the center pixel you have a very high value, and all the neighbor you'll get a very low value. So what will happen, right? So when you have when a small changes happen in the image, it will be having an impulse response. So through this, when you apply a small change, it will have a huge response here, because the negative value and the center value, it will react to each other, and it will enhance something. So let's see here. So when you apply this, yeah, can you see it? This is the sharpening process, where you can see that every here, let's see in this camera, where you can see, right? So here it's just a plain box, you cannot see any borders, but here, because of sharpening, because of this characteristics we implied on this image using convolution, you can see a corner, it's very bright here, and you can see this area, it's much brighter and a better one. So this is much interesting if you want to sharpen your image in your selfie, or and you want to blur someone's face in your selfie. or something, you can use this nice characteristic and do your own code instead of depending on any tool or Android applications or iOS application.
See the convolution in action. I have created a notebook Jupyter for our need, and I loaded the basic libraries which we use in previous demo. Okay, now what we are going to do is we create an image and we create a kernel, then we apply the convolution and see the results there. After that we just play around how to blur an image. Okay, let's go. Let's name it as convolution. So the hash represents the heading. If you have one hash, a very big heading, and if you have multiple hash, it will reduce the heading size. Create an image. Let's create a binary image. So you have studied how to create a binary image. So I will do NumPy, and I'm drawing a rectangle on the image. Comma the point, the first point. Let's keep 20, 20 and 80, 80, and color, yes, 255, and the thickness, right? So previously we haven't given thickness. Now I'm going to give it some thickness, so I will give some 2. Yep. Then I'm going to see the image see map. Great. Set enter. Yeah, you can see the image now. So if you want to reduce it, let's keep it 1. Yeah, you can see an image, a rectangle. The width of the line width of the rectangle has changed. Okay, now we have to create a kernel. As in our slide, we have seen how a kernel looks. Zeros of, let's have 3x3, 3x3. And now I'm going to change only the middle row and giving value 1 for all the items in the middle row. So in a NumPy matrix, how to change some indices, you can type kernel and you have to give the row indices. Now the middle row should be 1 because 0 the first and 2 will be the second, and the other rows, right? So here we can give 0 and equal to 1 and copy paste, and going to convert the column to. Okay, so yeah, this is one way to give. What you can do, right? You can give kernel 1, colon and equal to, you can give 1, 1, 1. Okay, this is some easiest way to do. So to access one pixel, you can do. To access a row, you can give row indices and you give a colon, which will show that you have represent all the items in the row. Now if you want to see the kernel, second row will be 1, 1, 1. Okay, let's do the convolution. So convol image equal to CV filter 2D. The name is a little different here, but the purpose is same. The source, what's our source here? Let's get the name of the source. Okay, image is our source, and the kernel, and second one is the d depth. Try to keep -1, that it includes all the depth, and the kernel, yeah, kernel. And yes, let's see the image too. Plot im show convo image, comma, what's the value here? CMap gray. Okay, you can see here, the values on here are blurred, but it highlights this value, the row, because the character of the kernel is a line, so it is highlighting the line on the top, but it is reducing the line on the right and left side. You can see. Let's play around, right? So instead of keeping a single row, okay, what I will do, right, I'm increasing the numbers, okay, number of the kernel size, okay, I'm increasing to 7, and yeah, 7, and I'm going to give the size, okay, changing the size here, let it be 3 rows and 7 columns, and the second row will be changed here. If you want to see, yeah, this is the new kernel, and let's see how the image changes. Yeah, okay, you could see right now the highlight of the line top and bottom is very high, but it's low. Let's see a much better way. So let's apply a threshold here. So I'm going to have the same image, but I'm applying a threshold to avoid unwanted pixels like this. Let's keep a threshold 255 above, because I want, because this line you'll get more than 3 times, so definitely this, we want to preserve these lines, and we want to omit these unwanted artifacts on the side. So enter. Yes, we can preserve this. You can see, right, how our line filter will preserve this. Let's now apply a vertical line. So I'm just applying a vertical line here. So you want to see the kernel here, this is a kernel, and now when I apply a transpose to the kernel, this will become a vertical one. So a vertical line in the center, and all the left and the right should be 0, and I'm applying the same here. So same, I'm copying here and pasting, and here I'm applying NP transpose. NP transpose, which is applying a row into column and column into row, and I'm pressing shift enter, and you get the vertical line. So in the here you got the horizontal and here vertical. With respect to the kernel's information, kernel pattern, we got the image, we preserve the image. Now we will see how to blur an image. So let's create the blur kernel equal to np once. Let's have a shape of 11,11, and I already told, right, we are going to divide that kernel with the square of the image to make smooth and easy operation. So kernel divided by, all the pixels in the kernel will be divided by 11 square, and I'm going to see the kernel. Okay, it's a smooth kernel, every element has same numbers, To avoid making a bigger image, we are dividing this number with 11 square, common number for everything, and I'm hiding this. Okay, let's load an image. Gray image equal to, I'm going to read our logo image. You can type LO and you can press space, control space to auto complete things, and I'm going to load a grayscale image. So I typed it and shift enter, and you'll get it. Now we are going to apply our convolution, CV2, filter 2D, gray image, comma, -1 for the d-depth, and kernel I'm going to apply, and I'm giving this as a name, blur image. Now we are going to see all the images to one shot. So plot, figure, I think you also familiar with these things. Fixed size 25, 25, and plot, subplot. I'm going to have 1 row, 2 column, and this is the first image, and plot. I am show. I want to first show my image, so gray image, comma, cmap equal to gray, and yes, Control C, Control V, and changing number of plot here and the indices for the plot, and here I'm going to show the blur image. Shift enter. Cool, right? You can see the image, the logo image, and the blurred image of the logo. Let's see how to sharpen the image using convolution. Let's have a heading, sharpen an image. I'm making it mark down here, so shift enter, and now let's see. So in the slide we have seen what is the kernel of the sharpening. And numpy array, so it's like I'm going to have a 3,3 numpy array, and the first row 0, -1, 0, second row 0, 5, -1, and third row will be 0, -1, 0. Let's see the sharpened kernel. Okay, you can see here this is a sharpened kernel where you can see the center we are giving more importance, and if anything which is seeing nearby, if anything we are there is a huge dip, it's like the diagram will be coming down and increasing, so this format. So if some small changes, it is sharpen the changes. I'm going to copy the same blur image and I'm going to change to see the images. So just changing sharp image here, grayscale, and I'm changing the kernel name. Then I'm changing the plot images. Okay, so the same blur image I'm copying and I am saving here. Shift enter. Yeah, you can see the sharpened output. It's really cool, right? So all the corners they have sharpened, and you can see a nice sharpened all the lines and things. Yeah, so in this way we get sharpened, and you can control the sharpening by changing the values. Instead of 5 you can keep 3 to give less sharpening, or if you want to have more sharpening, you can increase to 20 or 30. Yeah.
Edge detection is one of the part of convolutions application. So let's say Sobel edge here. We in the previous session we have seen how to increase the sharpening of an image, how to blur an image using convolution. Now it is one mature stage of convolution. Here now we are going to find the edges of the image. So edges in the sense, in an image you find the all the corners of the object or circumference of the object. So let's take this on gray image and I'm applying a convolution. This is the kernel weights of a Sobel edge. So you'll get 0 0 0 at the center, and you'll get -1 -2 -1, and in the bottom 1 2 1. So it's a positive one and giving more importance to the center one. So we are applying this kernel, and once you implying this characteristic, this will be the output of the things. You can easily notice that it is taking the horizontal edges of this image. You can get here you get these horizontal edges here, but we are missing the vertical edges. Okay, so through these we can easily get all the horizontal image. You can see here when a plane image comes, the bottom also same value, center also same value, and the top will be also same value. So this row will cancel each other to be the same value, and this row. But when it changes, when the horizontal side, so in the top will be a different color and bottom will be a different color, and once you apply this Sobel kernel, it will not cancel each other and it produces some value, and this value is highlighted here. Let's see the vertical operator. The same thing, we have applied a transpose and we have just rotated, and you can see here -1 -1 -1 and here 1 2 1. So here we have just applied a transpose of this kernel, and this will find the vertical edges by applying convolution. So convolving this image with this vertical operator, you will get this nice vertical edges. So you can see the same one here. You'll get only the vertical edges. Where we missed here, we didn't get the nose, but you get the nose here. Okay, now we are going to combine the both horizontal edges and vertical edges. So this is our horizontal edges we have taken by our horizontal operator, Sobel operator, and we are adding the vertical operator on the same image, and finally we'll get a complete kind of edges. Okay, so you'll get a whole edge of all the horizontal and vertical packet, just adding this image with this image, the horizontal edges and vertical edges, and we are getting a final edge. So let's see this in our HandsOnCV. We do it ourselves and we'll see the result.
Now we are going to see the edge detection in action in the same NumPy notebook. I'm going to create a markdown now as edge detection, and I'm having a small heading as Sobel edge detector. Okay, we are going to use the same logo image, so I want to show the logo image. CMap gray. Okay, nice. What we are going to do is, now we'll design the Sobel kernel, then we apply the kernel on this image, and let's visualize how the kernel looks. Then we will see an interesting edge detector in OpenCV, then how to do a pencil drawing using OpenCV. Here now I'm going to design a kernel. So one thing you keep in mind, right? So always document your code, then it's easy to revisit your thing or to explain, or while you want to understand what you are doing. So kernel, now there are two kernels. Now I'm going to create the horizontal kernel. NumPy, let's keep NumPy zeros of shape 3,3, and I'm going to give the first row equal to 1, so the -1, -2, -1, and the second one, just want to copy this and paste it twice. First row, here everything is 0, so I don't want to do it because it is already 0, but to understand better, do it. And here everything is positive. Yeah, let's see the kernel. Okay, cool. Okay, now we are you can see, right, already I have explained in the slide that that we are going to get the edges. So edge means you should have a difference on the horizontal plane. Okay, horizontal in the x-axis, you should have a difference. If it doesn't have any difference, it will subtract each other and it will become nullify. So if any difference is there, and you can see the changes, and it will produce an edge there. Now I am going to create another kernel, which will call it as vertical, and I'm going to have a vertical, but what I will do, right, I'll just apply a transpose on this kernel, horizontal kernel, and I will show it for you. Okay, this is a vertical kernel. Okay, now we have two kernels, Sobel kernels. Now we are going to apply on the logo image. First one is image horizontal. Let's have a good name. Horizontal, edge horizontal equal to CV filter 2D gray image, comma -1 for the depth, and the kernel will be horizontal kernel. And I'm going to apply the vertical kernel, so I named it as edge vertical. Same CV filter ID, you can copy paste the previous one, -1, and here the kernel vertical. Okay, now we are going to see both. So what I will do, right, if we want to see more than one, you have to create a figure, then subplot it. Fixed size should be, yeah, 2 images. I'm giving 25 × 25. Then subplot the edge horizontal. Sorry, subplot I had to give 1 row, 2 column, 1 first image, and plot show edge horizontal. Then I'm going to see the vertical too. Save, enter. Okay, it is coming. What I missed? Yes, I missed the CMap. So it is giving its own color, but I'm going to say that this is grayscale image. Okay, now you can see this image, the left hand image. You can see here the image, it only highlights the horizontal part in the image. No, there's some vertical part, it is not coming in. This is the best place where you could find here that only the horizontal line coming. It doesn't have any this vertical lines here. So interesting. Okay, same thing we see here, the vertical uh, kernel. You can get the vertical here, but you couldn't get the horizontal here. This is the best example on the camera side where you will get only the vertical lines and you miss all the horizontal lines. The best thing, you can see the nose. Yep, here the horizontal comes, here the vertical comes. Yeah, it's interesting. But we want the both. How to combine it? Combining both. It's very simple. Okay, so what we do is edge equal to, let's name it as Sobel edge. Sobel edge equal to NP absolute of the left hand. So the left one is horizontal one, so edge horizontal plus NPA absolute. Why I made absolute here, right? Sometimes it may have some minus value, some higher minus value, so negative value. So better take absolute, which converts all plus and minus to positive. Vertical, and I'm going to see the image. I am show Sobel edge and C map gray. Shift enter. Wow, how is it? You can get the whole camera, you get everything, but you miss something here. Yeah, something here, and you miss something here, I think so. Yeah, something you are missing, but it's nice, right? This is Sobel edge detector. You design your own Sobel edge detector. I want better edge detector because I don't want some missing things. The name of the edge detection is Canny edge detector. I'm not going to explain the theory here, but let's apply how to do this. So Canny edge equal to cv.canny and the image, my grayscale image, and threshold. You can play around later with this threshold. That's all, and we will see the output. Canny edge, C map gray. Shift enter. How is it? Okay, you don't need to do all the things what you have done. If you have an OpenCV and if you know, so you should know what is edge, and you understand what is edge here and how we produce this edge by convolution. And now really, if you want to have a perfect edge, please use Canny edge detector. This perfect and significant research has done to bring this thing, and it is freely available in OpenCV. Now we will see a nice application in convolution and edge detection. Pencil sketch. Okay, so you have seen in your mobile application a lot of pencil sketching images, and you play with your image, your selfies, and you can post it in a WhatsApp status, Facebook, everything. that you have done, not any application. So let's do that. Pencil sketch by HandsOnCV. Okay, I'm changing this into a markdown. Okay, it's very simple. We have to invert this image to a pencil sketch. Okay, pencil sketch equal to CV bitwise not. I'm just changing this image, like all the zeros should be 1 and all the 1 should be 0. That's all. My gray image, no, sorry, not gray image, my can edge deduction edge, and I'm plotting it. CMap, shift enter. How is it? It's nice, right? So you can try in your own image, in your own selfie.
Please like and subscribe my channel. In next video we will see how to do video processing, how to read a video, see a video, and how to do a background subtraction, very interesting one. Then also we will see how to do your own face deduction and the eyes deduction on the faces. Thank you.